So period 1 and or period 6, if this ends up being you today. Our goal is finish examples on 4-3. How many of you guys are at least 75% done with 4-3?
75%.
At least. Okay, so like a third. Okay, the rest of you guys will be maybe a little bit ashamed today as you realize how easy it is. This is how easy I believe it is. And then those of you that were working on it, you might have gotten stuff in here or there because some of these things are unfamiliar. But the nice thing is, in some ways, hopefully you'll be able to bust it out tonight if you didn't already. And the rest of you guys can hopefully even maybe start on 4-4. We do have, I think, 3 days on 4-4. So we have like half of today, tomorrow, and Wednesday with that homework due on, yeah, there it is, Thursday. But put in parentheses, okay, 4-3, do them. So here's our limit definition of an integral. And technically, if you guys realize there was some space on this fiber card because there is another way of writing it that maybe you realize they didn't match up perfectly. I told you to go back and look. But there's a bit of a difference. Now, most of it's the same. But you notice, okay, hold on. There is a particular f of x in both of these, in letter A and letter B. There is a particular f of x that's being used that we kind of have to decipher. C, f of c. So that's different in each of these. But what else is different from the definition of a definite integral? The limit of Riemann sums, besides just that they've used some particular function. And the examples below and the forever part above. You guys wrote that whole thing out and didn't see any difference? It's little, it's small, but it's yet kind of big. The limit as, instead of n going to infinity, instead of the number of rectangles going to infinity, it has this weird double line thing. Does anybody remember from pre-cal? There were double lines around the magnitudes of vectors. The magnitudes of vectors, there were double lines, the how muchness. Now, this one's a little bit different because it's the how muchness of delta. You can think how muchness. Who's delta? Yeah, it works. Like magnitude of an earthquake, it's like that. Because I'd say like, okay, how much force, but then it could also be how much speed, and it could also be how much acceleration, and it can also be how much work with joules. Anyway, we'll just say how much. Greatness. Okay, but anyway, if that's what this is, think magnitude, that's okay. But what's the little delta? Greek letter, yeah, but what's it usually mean? Change. So, how much change? What does that mean? Well, technically it's called a partition. Maybe you've heard the word partition before, maybe you haven't. It does kind of happen with computers from time to time. Or it's mentioned in context of computers from time to time. But everything else is basically the same as far as going from 1 to n, some number of rectangles, f of c sub I, these the special x that's in there, delta x sub I, but delta x. Do you remember what delta x in the, I think it's in the same section we talked about how to approximate the rectangles and trapezoids. What's a delta x label in our area formulas? Base. Exactly. Why is no one else looking in their notes? Why do we take notes? Anyway, if you look back, delta x was the base. So it's as the change in the delta x, as the change in the subintervals goes to 0, because the more and more and more and more and more rectangles you fit in, what happens to those bases? AKA going to 0. Now, there was this whole debate. It was a philosophical debate because mathematicians were really kind of like philosophers way back. And so the church was like, you're going around preaching heresy. Happened in science, happened in math. The church is not always, the church as an institution, as a somewhat back then political body has issues. It's not always perfect. God is perfect, not necessarily his followers. Crusades, going until then. Anyway, So, back in the day, it was a huge debate as to whether or not calculus should even be talked about, because it was the idea of accumulating infinitesimals, and infinitesimals were known to have absolutely no depth. It was like one dimensions. It was completely thin. And so the idea of, to be honest, an integral, or even the idea of limits to some degree, but especially an integral, is saying we're having these rectangles get thinner and thinner and thinner and thinner, and basically going to a base of 0, which is impossible to still have thickness. And we're accumulating these infinitely many infinitesimals, these infinitely thin. So basically you're putting together all these one dimensions that by themselves have absolutely no depth, and you're making the second dimension that does have depth. And they were basically like, heresy, you can't have something out of nothing. It's like creation. Anyway, forget that. It still happened. People persevered, and it was seen and known to model at least somewhat of the phenomena that we use math to model. But this whole idea of infinitesimally thin, that's what this is. This is saying infinitely many, and this is saying infinitesimally thin. And technically, this whole idea of Riemann sums both are true at the same time. Yes, you're having infinitely many rectangles, and yes, they're infinitesimally thin. Anyway, all that to say, don't get confused if the notation looks like this instead of looking like this. Don't get confused. Same thing, basically. Just a little bit different way of saying it. And so down here, I said just a second ago, don't get confused by all the rest of it in here. You just need to basically decipher who is your f of x. Now, wait. It's not an f of x. What is it? It's an f of who? C sub I. So look at the C sub i's as what? What did I just cross out that I changed to be C sub I? X. So look at C sub i's to be x's, because I'm doing a definite integral. And I'm doing it of a function, but instead of the C sub I, what am I going to put in if I'm going to put a dx at the end? It's not going to be C I, it's going to be x. And 4 minus x squared. Now, if they give me bounds, I could go ahead and put in bounds. If they don't give me bounds, well, I guess technically it's an indefinite integral. So we could leave this one indefinite, but let me go ahead and model for you in this one. What if they were to say something like 4x within negative, I better not tell you that one, because you don't know how to do that until you get to Calc 2. And improper integrals, let's say 1 to 5. I was going to go over 0, but 0 is a vertical line. Maybe some of you want to think about why that could be an issue. But if they give me an interval, if they keep this expression going, then I can get a bottom bound and a top bound. I know where to start and stop. That doesn't show up in here at all. It's separate. And then I can say that my function is who or what? 3 over x. Okay, more than Adam gets it, right? And Mariah? And Kathleen, the rest of you guys are checking. So that C sub I is just a snazzy name for an x, that's all. It's just a snazzy name for an x. Now, over here, wait a minute, hold on. First of all, they didn't really give an area, but some of you are probably assuming what areas should be shaded. I believe in the book, those of you, there were a few of you that were working on homework. Did they shade that area for you so you knew exactly what to do? Sometimes. Interesting. Okay. I think sometimes you were actually showing the area. Were you? They gave you an integral and you had to think about it like area. But these ones, they're giving you the picture, and all they want is, okay, what kind of integral could you write? We're still working on that forever hard. So integral means, a definite integral means, we have a beginning, we have an ending of a region that's defined by a function towards the horizontal axis. So what would my function be for this integral, guys? Yeah, it's as easy as 4 minus 2x, but we'll come back. We haven't put our bounds in. The question, what would be my function for this one? Could I do y minus 2 squared? Sure. Okay, but if I do, what needs to change? If I need to, remember, an integral needs an integral, it needs a differential, and it needs a function in the middle. It's like a sandwich. And that function, dy, because it's in terms of y. Now, what are my bounds going to be if I'm in terms of x? I need x bounds. We haven't talked about this. 0 to 2. But everything's changed. Now I'm in terms of y. So what are my bounds going to be? Got it. So we use our y bounds when in terms of y, and we use our x bounds when in terms of x. And so that means if I ever have to change this differential to something else, a t or a u, use, I would have to change my bounds to reflect that as well. Do you see how I busted out examples? Look at the math. So then number 3. Number 3 says now it's your turn to take an integral and solve it using, I told you guys on Friday, you are not supposed to be doing any antiderivatives in this section. I know Jared, the OChem tutor, used an antiderivative. I know I showed you how to use an antiderivative. You can't even use your calculator. They put in A's. That's so AP-ish. This probably would be on the calculator section, and you'd be like, well, right? You're like, ugh, if only they were numbers. Well, they want to make sure you know the idea. Now, hold on. We talked about this well, in general, we talked about constant functions and what they make. But if worse comes to worse, just think about the function. Think about your basic graphs and discover it for yourself if you don't remember. Isn't y equals 4? Isn't that a horizontal line? Wait a minute. I can't put negative a and a on a graph. Okay, sure you can. Don't I put up random numbers on graphs all the time? Didn't I put up an a and a b just the other day? So can't you throw up a negative a? Wait a minute. Okay, hold on. If you put up a negative a, what needs to be true about your positive a? Same distance on the other side. Okay, so maybe we don't know what it is, but we can still state it. And if we can state it, can't we still show our rectangular area that we're trying to find? Oh, that's why it's geometry. It's just a rectangle. And we even put the area of a rectangle on a forever card. Base times height, or maybe height times base. But I can't say what this is. Well, they don't want it to be a number, you silly goofs. If you look at the multiple choice options, if it was a multiple choice, there would be a's in it. What's your base? 2a. Do you remember in pre-cal once upon a time there were nasty graphs and you didn't exactly know what the bases and the heights were? And you kind of had to look at it being like x on one side and x on the other side and y going up. You didn't like it, but it was building you up to right now. A on one side, A on the other side. The base is 2a. What's the height? Oh, we know that one. So it's as easy as, no stress, it's an area. And the area is 4 times 2a. Oops. So then therefore, what's my definite integral? 8a. Dun, 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 dun. Always? Always. For integral of 4, from any negative to positive, exact same number. And it's a rectangle. It's always going to have a base of 2a. Now, hold on. Letter B. Is he a little bit harder? Yeah. But tell me what you know. What do you see that you know? Absolute value. Looks like a V. What do you see right in front of that absolute value? Which means a vertical flip. What do you see outside the minus? Which means a vertical shift. So it's been shifted from 0, 0 up to some distance a. Some distance a. It's going downwards. Now wait a minute. This is great and all. Okay, yeah, fine. It's going to be a triangle. Maybe you see it. But some of you might be like, okay, that's great. I see that the height, right? I see that the height is going to equal a. But what's the dilemma if we need an area of a triangle? We need the base. So what do we need to think about? Triangle, we need area equals, not on our forever card, but I'm hoping you know it. Okay. We have the height is a. We need the base. I'm shading the base, but we haven't labeled the base because we haven't thought about it. But what do we know about the base? What marks the beginning and end of that? How do you know that, Kathleen? Because of the angle? Yeah, if you look at the function, but you have to, I would just say keep explaining it. Aren't they x-intercepts? Aren't x-intercepts when y is 0? What would it take for this to be 0? I would have to have a minus a, right? So you could actually solve for it, but yeah, the only way you could get it is if you have a minus a, but an absolute value, remember it's plus or minus, there are 2 different possible ways of getting it, which we can see in our picture, which is nice. So the nice thing is, what's the exact same thing about our base? Yeah. 2a again. So this one may be a little bit harder because there's more a's, but it's still just a geometry formula we're plugging in. So we have 1/2 base times height. The 2's end up reducing, and don't we just end up with? Now, those of you guys that have worked on homework, are there some where you actually get like numbers because they've given you that? Probably, yeah. But what I'm trying to get you to do, and what the book's forcing you to do at least sometimes, is not just go to your calculator. I showed you the cool feature because I wanted you to be thinking about it. I wanted you to see like the calculator shade the area, the definite integral, just the area. want you to be solving with geometry because the AP is going to force your hand, like you see these examples. There's no way to plug this into your calculator. Well, I guess you could graph it and then look at it, but that's what we just did. All right, section 4.3. I'm going to go ahead and, as you guys start taking notes, we're going to skip the motion packet for right now. I actually don't know why I put that right there. I think I want that after section 4.3. Because we haven't even learned how to do definite integrals by hand yet, as far as apart from geometry. And geometry only works if you have geometric solids, geometric figures. Those of you guys watching the video, so sorry. You might want to pause it right here. I'm going to rearrange just for a second these motion problems to be down below 4.4. I'll be right back, though, if you just want to be patient. We'll just put it right here-ish. And then we'll come back. Actually, maybe I'll just undo. I skipped a lot of stuff when I moved that. And so I might have a better place for it later. We'll just leave it for now. So if you guys are looking through notes, just skip that motion stuff for right now. Technically, this first page in section 4.4, technically we already wrote down 1 and 2 and 3. 4 I'll fill in quickly, but once again, we're going to go back to that motion packet once we have some more skills as far as actually solving. So graphically, we talked about, okay, we have that little function f. We have some sort of random a to some sort of random b. We're trying to find that area. Number 2, solve with geometry if that area happens. And I'm going to do the most common one, that's the trickiest one. If that area just happens to look geometric, which they're not going to give you the picture. That's something just like we modeled. You're going to have to figure out by drawing out what you see. This one is the trickiest one, and this one is the square root of r squared minus x squared dx. Negative r to r is one way of seeing that semicircle. It could go from 0 to r and be a quarter circle. Either way, that's a semicircle with an area of 1/2 pi r squared. Anyway, they could do triangles, they could do rectangles, they could do trapezoids, but semicircles are the hard ones to see. But if it's not geometric, well, we can't even have like a snazzy formula if we can get the picture that we can use from our olden days. If it's one of these funny ones with a curve, and I'll just use an example of maybe like maybe a reciprocal function. And if we wanted an area from A to B, so far without using our calculator, all we've talked about is, hey, you can use these Riemann sum, guys, R-rams and L-rams and M-rams. You split it up into n equals 4 or 8 or 10 or 100 or 1,000. If you're using a sigma, man, I could actually even do 1,000 rectangles if I figure out my sigma notation really well. And I could do an approximation. This one's technically an L-ram. Just want to do a little reminder. It's each subinterval we're hitting on the left and jutting out instead of hitting on the right and coming back in. But that can approximate the actual area. And we do things like A1 plus A2 plus A3 plus A4. With motion, we're going to talk about something like, we can do displacement, how far you've moved. A change in position is known to be the definite integral from A to B of a velocity. And you saw Jared, the OChem tutor, doing that. He put a rate inside the integral. And then he was able to come back out into the antiderivative. And you guys already know velocity comes back into position from the motion homework you did in 4.1b. But what you might not have realized is if we put bounds on that, a beginning and an end, and we get a constant number out, what that's going to be is a change in position. going to be an S of B minus S of A. And that's kind of introducing you to this whole idea that's coming in just a second as far as the fundamental theorem of calculus, how to solve any integral, not just a motion. So what we're left with right now, technically, is we haven't really gotten into the motion packet to see this, but we kind of saw that velocity went to position. The integral of a rate went to an original amount, not just in motion, but in any context. So how do we algebraically deal with definite integrals now of rates going back? We do have these properties on the other side that you guys have seen, at least that you have been trying to write down. I'm going to zoom in on that if you guys don't mind, because they're kind of small and the bounds are kind of hard to see. Maybe some of this can make sense if you just think about these are areas, an area that is spread between A to B, bounded by a function in the horizontal axis. But guys, if you go from A to A, have you gone anywhere? No, if I haven't gone anywhere, if I just said that the integral of rate is a change in the original, if you haven't gone anywhere, there hasn't been a change. That's one way of saying it. Another way of saying it is if you haven't extended the area at all, it's the first dimension, which has a depth of an area of 0. Which is why a few years ago on one of the sweatshirts I put on the back, hours of sleep a calculus student gets, and it was the integral from A to A of a function of that. Number 2, number 2 is kind of weird because aren't A and B's just random variables to represent random numbers? Except, I'm going to write over here, right, that all of these are talking about the integral of a function f of x for x within. As soon as I write it here, are A and B completely random numbers? No, because what's the proper way of doing an integral notation? What comes first and what comes second? B is going to be greater or higher or more positive than A, right? A is lower or more negative. B is higher or more positive. So if that's the case, why is this one weird? The lower is in the upper bound spot and the upper is in the lower bound spot. Now, that's not illegal at all. But what that means is in your area, instead of going from A to B, like we're used to, this one says, oh, no, you're going from B to A. You're going backwards. You're going the opposite direction. So if you're going backwards, if you're going the opposite direction, well, then we're going to need a negative to be able to think about going forwards. You're always allowed to switch the order of the bounds when necessary by throwing in a negative. It's just the opposite direction. We've already talked about how constants can come out when you guys do anti-derivatives. Bounds don't mess that up. With bounds, though, there is this extra property that to get from A to B, every now and then we need to stop off at, hit and check out, a C in between. But the crazy thing is, I just said in between, because in some ways it's in between going from A to B, but in some ways, C could be something way outside. C does not have to be in between A to B. So a quick reminder over here, C can be any constant. I would say just not equal to A or B. It shouldn't be equal to A or B, but C can be any constant. So if you're doing area from A to C, from C to B, add those two areas together, you will always get A to B. Some of you might be like, well, what if C is beyond? Or don't you have too much area? Yeah, but then this would be backwards, so then it would be subtracting. It would actually work out this way. And then number 5 just says, hey, that sum and difference property is still totally false. Kiddos, what we weren't able to get to today is the very, very, very beginning of working with definite integrals algebraically, not going to areas, not going to graphs, not going to rectangles, just working with them. And I might be able to show you a couple things with those examples in just 1 second, which would let you honestly get started on that homework. But then this is the main concept of section 4.4, the fundamental theorem of calculus. Don't worry, it's going to be a front card and it's not this page. But the fundamental theorem of calculus says this is how you solve front hand low graphs, and anti-derivatives are coming back full force. So for tomorrow, have your 4-3 done. Maybe just start 4-4 and like these basic, you don't need to know the fundamental theorem of calculus quite yet. There's giving you area pieces and having you play with them. But then review your anti-derivative rules. Because I graded your integration quizzes. You're going to be getting them back tomorrow. You're going to see what anti-derivatives you are or were not good at. Hopefully you're better now. But please look over those anti-derivative formulas. Guys, check out how easy these are. What did I just do? I plugged it in. So I was able to pull out the 3 and figure out the area under f of x from 1 to 4 and subtract the area under g from 1 to 4. But no. This is all put together. But no. You're able to split it all apart from those cool properties we saw with antiderivatives. So wait a minute. What do you think this one's going to be? There is going to be a 2. There is going to be a plugging in of 2. But what's missing? A negative, because the bounds are switched. Oh, this one's going to be negative 4. And then this last one. Oh, I have an extra clue. I know from 1 to 2, only part of this area is negative 5. So how do I 2 to 4? That's the rest of the area. Hold on. So 2 is the total, and negative 5 is part of it, and I'm trying to find the other part. Ooh. Maybe this one ended up being 7. Ooh, muy interesante. Maybe some things for us to ponder. Do you have to have it totally solid right now? No, you don't. Guys, we're done for today because I'm going to run up and grab